Hi there, and welcome to Mr. Carlson's lab. Some time ago I took on a restoration project, which at this point has really turned into quite an in-depth restoration project. Really don't want to get into that too incredibly much because that's an entire video within itself and I don't want to spoil any surprises. So let's just call this thing I'm working on a device. So in order to work on this device, I needed to design an active RF probe. So this really is a purpose-driven device that I created just to do this job, but I figured maybe you guys can benefit by this, so why not share it? So let's take a look at the schematic diagram and some of the specifications. This is the active RF probe schematic that I've come up with, and I'm very pleased with its results. Now, this was originally a very purpose-driven device, and I had no intentions of even making a video on this. I just put this thing together to get me through a portion of the restoration that I'm doing, and this needed to be flat through a small frequency range. But since I was designing this thing, I figured, maybe you guys can benefit from this as well. So I tweaked the circuit a little bit and played with the layout and really extended its frequency range. And of course, the whole magic in an RF probe is to keep it as close to being flat for as wide of a frequency range as possible. So that's what I toyed with when I was building this. Now, this is a one-to-one active RF probe. So if I put 20 millivolts of RF on the input here, I'm going to get 20 millivolts into 50 ohms at the output here. So really, I can take a very high impedance area over here and drive a 50 ohm load with it. Really is what I can do. And I'll get into explaining this here with the 50 ohms quite shortly, and oscilloscopes and everything like that. So there is one catch-22 if you build this thing, and I've looked at this on spectrum analyzers and spent a lot of time critiquing this circuit. So if you copy this circuit, if you want to get the same results that I have, you have to build this almost identical to the way that I've built this. We're very, very close to, and if you haven't, then you're going to need to use a spectrum analyzer and sweep this thing and make sure that it is flat within your usable frequency range. All right, so component placement, trace length, capacitance, everything like that, inductance in the circuit, everything really plays an important part in keeping this thing flat. As you get higher and higher in frequency, lead length of components start to matter, trace length matters. There's a lot of things that really start to change. Things get difficult as you get higher and higher in frequency. Some things get difficult, some things get simpler. But when you're building an RF probe, the whole trick is to keep this thing flat, as flat as possible. And if you change component values or move things around, of course, this is going to move. You're going to change this. If you're looking for a very small frequency range that you want this thing to be flat within, I'd say that you probably toy with a layout, and if you say you only need a couple of megahertz, which is basically all you're going to really need anyways. If the amplitude changes and it's not completely flat, usually an amplitude change within a couple of megahertz, it really isn't too much, as long as it falls. For myself, I really don't want to exceed too much more than a dB and a bit of variation. All right, because if you start at the screen here and you're sweeping, you don't want it to look like a linear pattern. You want it to be absolutely flat, right? You don't want the pattern to be like this or like this, because if you're aligning something, if you're looking, just say you're sweeping this on a spectrum analyzer, okay, you got your tracking generator going to the input, and you've got the output of this going into a 50 ohm input on your spectrum analyzer, right? You turn this thing on and you look at the response pattern and it's like this. Well, if you're trying to align something with a response pattern like this, you have to compensate for this response pattern in what you're aligning, and that is extremely difficult to do. So of course you want this thing to remain completely flat, all right, from the start frequency to the end frequency, and that way you know that when you are doing your alignment, the device you're using to do the alignment, this active probe itself, is flat, all right? And if it's flat, then you know that your response pattern that you're going to see on the on your spectrum analyzer is going to be correct. If you had a response pattern that looked even, but it was like this, if you were to flatten that out, all right, then it would go like this, right? Because you're lifting this end up again. So it's very important to have an extremely flat response on this thing. As I say, I'm not so concerned about amplitude variation between the input and the output, as long as that amplitude variation is flat within the frequency range that I am using. So say, to give you a quick example of what I'm talking about to maybe lessen confusion here, just say I'm sweeping between 40 and 45 megahertz, and that's what the intention of this originally was, okay? If I put 10 millivolts in here, say, all right, for example, 10 millivolts in here at 40 megahertz, I need 10 millivolts out here at 40 megahertz into a 50 ohm load. Now, I don't touch anything here. I roll the frequency up from 40 to 41 to 42 to 43, all the way up to 45. When I get to 41, 42, 43, 44, and 45, if I have 10 millivolts here all the way along, I want 10 millivolts out here into 50 ohms all the way along. And if it's like that, my response pattern is going to be flat. So just say if I was looking at this on a through a tracking generator in a spectrum analyzer, just say at 40 it was 10, all right, at 41 it was 5, and then the rest it was 10 again. If I was to look at my response pattern, it would be like this, but it would have a dip in it at 41. So if you have that dip, it makes it extremely hard to do an alignment. And again, that's the magic of probes in keeping everything flat. And spectrum analyzers are designed to be like that. And that's what makes them so special, is that you can use them for measurement. If the amplitude went all over the place, it would be a useless device, right? So you're going to have to build this thing as close to the way that I built it as you possibly can. For a very small area, if you're using a very small area of it, you might be able to get away with just doing this. Chances are, if you're building this probe, you're going to use a spectrum analyzer. You got a spectrum analyzer at your disposal anyways. You'll be able to check it. And I'll show you how to check this on an oscilloscope too, all right? And that'll make things a little bit easier if you just have an oscilloscope. So of course this is designed basically an AC coupled circuit here. All right, we have a capacitor blocking any DC coming into this thing. This is an RF probe, and I'm just using this thing for RF purposes. All right. So I'll start with the schematic here. This is a 3SK74, and this is a dual gate FET, all right? I've played with all sorts of different FETs, and I found this VHF FET to work the nicest on the front end of this, all right? I have a whole bunch of FETs up here. Right here I have a 2N5486s. I have probably 500 of them in a little tray, and I tried a whole bunch of them, and I really didn't like the way that they looked, all right? They fell off a little bit early. This one here worked quite a ways down. For being a VHF FET was kind of interesting, but it worked very, very well. So I chose the 3SK74. I tied gate 2 to the drain because I'm not using gate 2. Now, whenever you see a dual gate FET, this is an N-channel dual gate FET, you can pretty much consider this thing, if you're a tube guy, it's like a tetrode, okay? So basically the drain is the plate, the source is the cathode. This would be grid 1 and grid 2, just like it says gate 1 and gate 2. It's really how these things operate. And these are kind of neat. You can use the G2, the gate 2, you can use that to turn the gain up and down of the FET if you want. In fact, in the future, I'm going to make a very extended probe with a very, very wide frequency range, and I'm going to try and keep it as flat as possible, at least within a 3 dB window at any rate. And that'll go way, 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 way up into the hundreds and hundreds of megahertz. I'll do that, and I'll just do it with off-the-shelf parts, and that will make a nice little project, and I'm sure it will benefit everybody. But what I was thinking of doing is almost making an AGC, an automatic gain control, to compensate for any kind of variation. So basically have some form of an op-amp or comparator circuit. Haven't thought about it too much, but really monitoring the output and monitoring the input basically through an amplifying circuit, high impedance amplifier circuit, and some diodes, rectify it, change it to DC, to the input and the output to some form of a DC level, and have that amplified and use that as gain compensation for the FET so that it keeps everything linear. Just a thought, possibly, I haven't really toyed with it too much. I might run into some design implications there, especially when you get down into the microvolt level. But at any rate, yeah, that's just something that's been rolling around in my head. So I might, toy with that. This turned out very, very well for what it is, and there was a bit of experimentation again because, lead capacitance and circuit variation, inductance, and all this kind of stuff. Things had to get moved around and things like that. In fact, I'll edit in a picture here, okay? Take a look at this picture. This picture is basically in the beginning of this. I created a circuit board, and you see all the flying leads and everything, and that's me just adding parts in and, you know, looking at a response pattern. I get things pretty close like this, all right? But then everything changes when you go from that to this here. This is like the next step. All right, so this next step right here is, you know, pretty much brought down to the circuit board level, and now I have a solid back plane on the other side of the circuit board. So really, it's a double-sided circuit board, and I haven't etched any of the copper off the bottom side, so it's shielded. And of course, that's going to add capacitance into the circuit, and that really starts to take effect as the frequencies get higher, right? So it turns from that into that, and then of course it'll turn into the end product, and I'll show you that here quite shortly about, you know, what the end product will look like. So there's quite a few steps in putting this thing together and you know, keeping everything perfect. So at any rate, so the input here is the 3SK74, and that worked very, very well. The input impedance, of course, is very high on a FET, and of course a lot of limitation is due to this 10 meg resistor here. You can most likely up that if you want higher input impedance. I stuck with 10 megs. It worked absolutely fine with that. I'm sure you could get away with 20 or even 30 megs, you know, something like that. I don't need anything higher than 10 megs. That's absolutely fine. All right, there's some 1N7511 Schottky diodes on the input here just to protect the gate 1 from, you know, getting zapped or anything like that. Again, this is going to add capacitance into the circuit. These diodes will add some capacitance, so you know, you can't have your cake and eat it too kind of idea. So I would much rather have the added capacitance than zap this FET, because I'm going to be using this for a whole bunch of things, and you know, if I'm ever in a tube circuit or something like that, I don't want to you know buzz gate 1. So I'll take that added capacitance and just leave that in there. If you're very sensitive and you wear ESD straps and stuff like that, you might be able to get away with eliminating these diodes completely, but yeah, it's pretty touchy business. So I keep them in here just because you know, it's going to keep this device happy, and I don't want to be changing them. These 3SK74 is an aging device by now, so I have a whole bunch of them, so I use that particular FET because I use the stuff I have on hand, right? So again, these here need to be 1N7511s. If you use normal diodes like a 1N914 or a 94152 or anything like that, you're going to find that it's going to load the input. You got to remember that diodes do leak. So you want to be using diodes that are like 1N7511s or something like that. When I put these on the input here, almost no effect whatsoever. Right down into the microvolts. Everything is fine. And this thing reads very, very precisely way down into the floor of my spectrum analyzer. So it works very, very well. And I'll display that here shortly again. So if you're going to build the input, use 1N7511s or something equivalent. Yeah, they got some capacitance, but yeah, what do you do, right? So I'm not so concerned about having the input voltage absolutely maxed, you know, absolutely the same as the output, as long as it's flat within the range that I need to be doing. That's really what I need this to be, how I need this to work. The op amp that this is going into is an LT1812CS6. It's a 100 megahertz op amp, so a little bit of this limitation of the, you know, the usable frequency range will be in this op amp right here as well. But again, this was a purpose-driven device for myself, and it works very, very well. So this is the op amp I'm using, and this here 1K potentiometer is just gain compensation, so I can again tune this thing to keep it flat throughout the range. A lot of fooling around in this little circuit right here, a lot of fooling around there to keep things absolutely flat, especially at the higher frequencies. So by putting a capacitor across this, of course, is going to enhance gain quite a bit. I didn't want that extra gain. In fact, the way I've got this potentiometer set up here, basically just the way it is, works very, very well. So no capacitors across it or anything like that for this situation. The BC817 here is what drives the coax up to a 50 ohm load. I have 4 50 ohm resistors here, so this turns into 50 ohms again. All right, just because of the size of the components, I used 4 of them. They're actually 49.9 ohms each. All right, very accurate. So 50 ohms, close enough. All right, so there's 4 of them, so I end up with 50 ohms here again. This here is the point 1 that couples it to the coax, and this here again at the end of the coax is again to you know, how would we say, get rid of any discontinuities in this small area of the circuit. This has to be tuned at one specific frequency in order to make things flat, or to keep them flat and get rid of a dip. And of course that's due to the coax and things like that. So I'll explain this capacitor here. This has to be right at the end at the BNC jack, where it goes into your spectrum analyzer or into any kind of a 50 ohm input on your scope. Now, scopes have usually 1 meg ohm inputs. The really high-end scopes, the ones that are used for RF work, usually do have 50 ohm inputs or a selectable 50 ohm input. If you have a scope that does not have 50 ohm inputs, you need to use a 50 ohm termination on a BNCT as it goes into your scope. You can't just plug this in. If you just plug this in without it being at 50 ohms, then again, the response pattern, the amplitude is going to change, and you will not get a flat response pattern, and there will be wild differences in voltage between the input and the output. This is no longer a one-to-one RF probe at that point, okay? 50 ohm termination, absolutely crucial if you're using this. Again, the whole idea of this probe is to take a high impedance input here and be able to drive a 50 ohm output. The spectrum analyzer that I'm using to do the job that I'm going to be doing has only a 50 ohm input, so that really is the necessity for this. My old HP 3585B has got a 1 meg ohm input, which is a very nice thing that Hewlett Packard did at the time, and many spectrum analyzers don't have that option. And the spectrum analyzer that I'm using does not have that option. You haven't seen that spectrum analyzer. Whether I'm going to include it in this video at this point, I'm not really quite sure. I have about 6 of those, and they're all just in various states of disrepair. So I've taken a bunch and made one really good spectrum analyzer out of basically 6 different units. So down the road, I'm going to go through and probably repair 6 different spectrum analyzers, and I'll probably make videos on that as well. Again, more lengthy videos. So it's all about time, right? So this is the positive 5 volt supply that feeds this circuit. So the op amp has a positive 5 and negative 5 volt supply. All right, the negative 5 is down here, the positive 5 is up here. This is a 10 microfarad ceramic capacitor. This is a 0.01 mic cap, and they're both on the same line. You can see we have a 1K and a 33 microfarad, or 33 microhenry, sorry, inductor on the source of this FET. So really, the FET is acting as a source follower, is all that it's really doing. Again, impedance conversion really is what we're doing. So this source, of course, drives the op amp here, and it comes through this 47 ohm and 0.01 microfarad capacitor into the base of the BC817, and of course we get drive out. This here is also very important, this 47 ohm resistor and 0.01 to ground this way. So basically the 0.01 blocks the DC, but we still have a 47 ohm resistor going to ground here. Very important to have that in order to extend that range as well. Okay. What else can I tell you about this circuit at this point? I think that's pretty much it. Yeah, that's it. So again, this is going to have to be kept as close as possible to the way that I'm going to build it. And what I'll do is I'll show you the layout next here. I have the layout on the computer, and we'll talk about the layout. And after the layout, we'll go and put the thing together and take a look at it on the analyzer. This is the circuit board layout that I've come up with for this probe. So this is going to be made on some double-sided circuit board. The back side of the circuit board, or the bottom side of the circuit board, will just remain a solid copper ground plane, and everything that you see here will just be etched on the top side. The little red squares that you see are just guides for me to drill through to join the ground plane layer on the bottom to the edges on the top, so really just joining the grounds. This is the input of the circuit here, so this would go to the probe tip. This is the 3SK74. The protection diodes will go here, and this is the associated input circuitry. Alright, this is that choke. This is the little op amp right here. This is where the signal path comes out of and goes into the NPN transistor. These are 4 49.9 ohm resistors. This is the coupling cap where it goes out the coax, and the coax will just go over here and out to the BNC connector that attaches to either the scope or the spectrum analyzer or whatever is being used. These two little squares here are where the positive and negative voltages come in. So this one here is the negative voltage, so this will be negative 5 volts, and this will be positive 5 volts right here. These are the 10 microfarad ceramic capacitors. And that really is what the circuit board is without getting into every single component. So what I'm going to do now is make the circuit board, and I'll be back and we'll take a peek at it and then I'll populate it. This is the etched and plated circuit board ready to be populated. I'll just put in a little TO92 package transistor here to give you an idea of the size. So you can see it's pretty small, lots of 0402 parts on there. So I'll get to populating this little circuit board here, and when I come back, we'll try it out. This is the populated circuit board. This is the 3SK74 FET right here. These are the two RF Schottky diodes. This is a 33 microhenry choke. This is that 100 megahertz op amp. This is a little variable resistor here. These are four 49.9 ohm resistors. This is a BC817. These two ceramic capacitors are 10 microfarad each. And there's also a bunch of 0.01 microfarad capacitors across the supply lines to ground. The frame around the edges is grounded, and it also goes to the back side of this circuit board. The back side is also just one solid plated piece, acting as shielding on the back side there. So that's the completed circuit board. So now to test it out and see how it works. I'm ready to test the performance of this little active RF probe, but before I do, I'll just explain how I have everything all hooked up. So the output of that little active RF probe circuit board runs up through a coaxial cable into this BNC connector right here, goes through this form of a BNCT into the spectrum analyzer, and this is that variable capacitor at the end of the coax that you saw on the whiteboard in the schematic diagram. Now I'm not going to leave that like that. This capacitor is wide open, and really like this, it's a noise magnet. So I plan on using this probe down into the microvolt region, and I don't want this open like this. So I managed to find this old Hewlett-Packard probe in my stuff, and it just so happens to have a thumb wheel with a compensation capacitor inside it that's really close to the range of this one here. So I kind of lucked out with that. So it's very easy to get inside here. You just undo this kind of a collar at the end of this tube here, and this whole thing just comes right apart, and I can get right in here and change components and do whatever. So I'll just get rid of this old coax, put some new coax in here, and I'll just put all of this into this thing right here. Down here is the signal generator that I'm going to be using. So I'm going to leave the amplitude output at 20 millivolts. And I'll just sweep the frequency range manually by spinning this knob here. I have it moving in 100 kilohertz increments, and you can see how nice and fluid that is, so it'll take no time to sweep the entire range. Now I could do it automatically and just, it'll move through the range rather quickly like that, but I just have more control by sticking my finger in there and just moving it like that. And we'll take a look at that here quite shortly on the spectrum analyzer. Down here on the bench is the little circuit board. This is the active probe circuit board. This is the coax coming into the circuit board from the RF signal generator with a termination here. There needs to be a termination at the end of the coax here, or of course the voltage readings will be all over the place. So this is the output of this active RF probe, and this is running back up to the spectrum analyzer. These three leads here are just the positive and negative 5 volt supplies and the ground to the power supply. Now I'm going to probably build a separate power supply for this, and it will be a linear supply. I don't want any switch and mode power supplies or anything like that, because that is just a recipe to introduce noise into this whole system here. And wanting to use this thing to measure right down into the microvolt region, and it does it quite well. This goes right into the noise floor of my spectrum analyzer. So I want to make sure that this is nice and quiet. Even two 9-volt batteries with some linear regulators, 5-volt linear regulators would be absolutely fine. But again, if I want to use this for extended periods of time, I can see that being a little bit rough on batteries. So power supply it is. So this is set up to start at 100 kilohertz, and the stop is at 70 megahertz here. I'll just show you that. So the start's at 100 kilohertz, and the stop is at 70 right here. This is 3 dB per division here. So I want to keep this within that 3 dB area here, so we can consider this bottom here at 3 dB down. So what I'm going to do is, by moving the signal generators, I'm just going to sweep the response of this probe. And we'll take a look at how flat it actually is. So I'm at 50 megahertz right now, so I'll slowly move down here. Not bad. So you can see the range that I have this very flat in, and I spent time with that just because I'm going to be using this thing within that range there. So again, you know, my range that I'm going to be sweeping is right here 40 megahertz to right here is 45 megahertz. But still a very, very usable range. So right down here, all right, that's considered the 3 dB down point right here, and that's at 61. See if I can, I'll just fine tune this here. So 61.300 megahertz or around that. All right, so I have this, you know, working at, 100 kilohertz here. I'm moving it in 100 kilohertz increments. So we could comfortably say, around about figure, 61 megahertz, all right, would be the top end of this probe. And again, that's at the 3 dB down point. And you can see right here is pretty much where it starts to come down, and that's about 50 megahertz right here. And it starts to come down in a nice linear fashion from that particular point. And you can see how flat it stays for a lot of the frequency range right there. So it's pretty much flat from about, I'd say 25 megahertz right up to 50. And, it moves down just a little bit here. Now, most of the RF probes, active RF probes that you buy are rated at, 3 dB down. So this is in a very, very comfortable range. Right now we're at about, 1.5 dB down, something like that. So it's really, really quite comfortable. Those little spikes that you see there is just the fluke signal generator. It's changing ranges and doing things inside there, so those little spikes show up on the spectrum analyzer. Nothing to be concerned about whatsoever. So all in all, a very decent frequency range for this, so that we know that the top end is about 60 megahertz or something like that. And we can see down here, at the bottom end here, it starts to drop down. So what I'll do in the next shot here is I'll just narrow this up a little bit, and we'll take a look at the bottom end and see where this really drops out. The spectrum analyzer is now set up to look at the bottom end useful range of this RF active probe. So the start frequency is at 50 kilohertz, and the stop frequency is at 1 megahertz, and that's at that edge of the screen there. So again, we want to keep this within this string of boxes here. We'll consider this line here the 3 dB down point. So what I'll do is I'll roll the signal generator right now, and I'll bring it to that point. And I'd say that's about the bottom end, and that's at 390 kilohertz. So this would still be useful for sweeping 455 kC IFs, even though we see that this is, in a little bit of a linear region here. The span would be so small if you were to say sweep 20 kilohertz, all right? So say your start frequency is at 445 kilohertz. That would mean the center would be at 455, and the stop would be at 465 kilohertz. That would give us a 20 kilohertz span. That span is so small that even though that we see that this is, somewhat in a linear region as we're moving this right now, it's still going to remain relatively flat, very, very close. It's going to mean absolutely nothing in the grand scheme of things here. And we'll take a look at that on my HP3585B and just take a look at how flat that will be using the actual tracking generator output on that spectrum analyzer. This is the spectrum analyzer I use for lower frequency work. So if I'm aligning the IF section in an old receiver, this is the machine that I use. This has a tracking generator output, which makes aligning IF really, really quite nice. This is a very, very nice machine to own. If you're ever looking for a lower frequency spectrum analyzer, I really suggest picking one of these things up. They really are great machines and very, very easy to use as well. So I've got the output of the probe hooked to the 50 ohm input of this spectrum analyzer, and what I'm going to do now is grab the input of the probe and attach it to the tracking generator output, and we'll see how flat this actually is. So here we go. There it is. You can see it's virtually flat. And that's a 20 kilohertz span. So the start frequency is 445 kilohertz. The stop frequency is 465 kilohertz, meaning that the center will be at 455 kilohertz. And again, the span is at 20 kilohertz. That's about perfect for doing a sweep on a 455 kCIF in an old receiver. So it works very, very well. Again, it goes down to about 390 kilohertz, and that's, about the end of the usefulness of this probe. I would modify it if I wanted to use this just continually for low frequency work below 390, but the way that this thing works right now, it's absolutely fine to use at 455 kilohertz. The output of this active RF probe is now attached to the input of my oscilloscope through a BNCT. On the other end of the BNCT is a 50 ohm load. The input of the active RF probe is still fed by the same signal generator sitting at 20 millivolts at 50 megahertz. Since it's a one-to-one probe, you can see it right here on the screen. What I'm going to do is reduce the frequency of the signal generator, and you'll see the sine waves start to spread apart, but what we're concerned with is the change in amplitude. Alright, so we don't want to see that much of a change in amplitude as we're going down in frequency. And technically, we can use this to gauge exactly what the frequency response of this probe would be if we didn't have a spectrum analyzer. And I'll just demonstrate that right now. So we want this to stay relatively close to 20 millivolts. Of course, there's going to be a few millivolt variation throughout the movement here. So here we go. This is going to go down at 1 megahertz at a time. And you can see it stays pretty constant. Throughout the frequency range of this RF active probe here. So you can get an idea of how to gauge this using an oscilloscope. You can see it pretty much stays within the screen there, and we already know what this is doing on a spectrum analyzer, so this is just a demonstration on an oscilloscope here. And that's how you would use an oscilloscope to determine the bandwidth of an RF probe. I hope you enjoyed the design and build of this RF active probe. If you did, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos just like this in the very near future, touching on all sorts of different aspects of electronics. Don't go away yet. I have an in behind the scenes shot of the way that this place actually looks during the build, so let's take a look at that. Here's a quick view of the lab, a behind-the-scenes view of what this place turns into when I'm building something. So this was a real spur-of-the-moment thing. I was working on the probe, and I figured I'll grab the camera and just show people what this place really turns into during a build. So it goes from really clean to really messy in no time flat, and it's everywhere. This place is a really big mess right now. But believe it or not, I know where everything is. That's the tripod that I normally use for my filming. All the cables on it there. I just rolled the chair under the bench. And this is the probe that I'm working on right now. And all the various different pieces of test gear that I'm using. I'm a real fan of dedicated screens. So each scope has its own function here, and I'm looking at all sorts of different things in the circuit. At this point, I'm actually sweeping this. So this is getting sweeped to 40 megahertz right now, really the top end of this spectrum analyzer. So this right now is 2 dB per division. So I'm very impressed with the response of this probe. Worked out really quite well. So I want to see higher than 40 megahertz, and that's why I have this set up right now. 59 megahertz is not the stop, that's just where I stopped it during its scan. and I use this spectrum analyzer on the top to see further up. So really what this is doing is this is sweeping the probe, and I'm looking at the response on this spectrum analyzer up here. Bunch of soldering irons going, and just voltmeter, and that's the microphone that I normally use. Right now I'm just using the mic on the camera, so I'm hoping this sounds okay. So there you have it. That's what this place turns into during a build. All right, take care. Bye for now.